Welcome to this video. In this video, I will be talking about surface codes in a brief way to show how these codes define the notion of stabilizers and how they are beneficial in quantum computation and quantum information to particularly ascertain the scaling property when the size of the system grows. So basically, if the size is large, then the number of errors will also grow, and with that the code size also increases. But these codes have nice scaling property, and also the commutation relation between stabilizers, the error syndromes, these are nicely visualized using these codes, and particularly these codes can be implemented using nearest neighbor interaction. So first let's dive into it. So for example, the first example is a code that is like a 913 code, but this is not Shor code because the stabilizers will be different in this case. So the 913 code means that you have 9 different sites, and on each site you have a qubit. So 1 2 3 4 5 6 7 8 9, and between these qubits now you have the plackets, which are these shaded and unshaded region, which denote which kind of stabilizers are being measured. So I have a placket which is shaded between 1 and 2. This means an x1 x2 stabilizer is being measured, and for measurement you need additional ancillary bit that I can denote with circles in between. So the number of stabilizers will also denote the number of additional ancillary bits that you need to measure the stabilizer or to extract the syndrome. This we have seen many times in the videos. So with this idea, let's go to a surface code which is the most primitive. It's just a 4 cycle, and it is of this form. It has 2 qubits d1 and d2, and you are measuring x1 x2 stabilizer and a z1 z2 stabilizer between them. So if I put ancillary bits between them, then there will be 4 qubits, and that I have shown here. So these are the data qubits. These are called data qubits, and a1 a2 are called the ancillary qubits. And between the data qubits, this yellow line represents a connection of z. This means I am measuring z1 z2 by using this ancilla, and I am measuring x1 x2 by using this ancilla. So how does it look in circuit is particularly shown here. So I have 2 data qubits d1 d2, and I am now taking 2 ancillary bits, and one of the ancillary bit is measuring x1 x2, and another ancilla is measuring z1 z2. And these kind of circuits we have seen in many times in the previous videos also. So with this, let's look at a detection code, that is 512 code, which is a surface code, and the idea is to understand what are the various components of this code and how error detection takes place. So if you look at the figure, so this is the figure. Here there are 1 2 3 4 5 data qubits. So these are data qubits, and between these two there is, if I look at the nomenclature, there is an x operation, and between these two, so these are z plackets and this is x placket. Now how do I write it? So I have 5 data qubits and 4 stabilizers. So I have 4 ancillary qubits which are denoted by this square here. So these are ancillars, and now I connect this white line to represent x measurement of stabilizer, and these yellow lines to detect a z measurement of stabilizer. So this ancilla, it's measuring basically x1 x2 x3. Now suppose a error occurs. Suppose I get a z error, which is a phase flip error in the central qubit. So this is a z error. What happens is that you can see that these yellow lines, they will commute with the with the z operation, but the white lines, which is x, they will anti-commute because they overlap exactly on one qubit where they are different. And this means that I will register a -1 in these two sides, and this will correspond to a syndrome where I will detect a stabilizer has gone off. Similarly, if I have a x error, which is a bit flip error here, for example, this I denote by solid color, then this x error will anti-commute with this yellow line, which is a z stabilizer, and I will detect a syndrome extraction circuit will detect -1. So this happens in a general way, and now we come to the idea of the toric code. So in the toric code, the idea is we have a code wrapped around a torus. I will come to it. So the basic idea is you have a set of qubits arranged like this, where the qubits are on the edges. So here these vertices does not mean anything. The edges are the qubit. So this is important. And then you identify the ends by introducing a periodic boundary condition. These ends are identified with each other, and this end is identified with each other. So this is basically a torus that is opened and cut open. So torus, cut open. And the idea is on this torus you will define the stabilizers in a certain fashion such that they form the plackets or the vertices. So let's come to the idea here. So here I have shown the torus here. So here is the torus, and as you can see that I have a periodic boundary condition where I identify this qubit with this one. So all the gray qubits will not be counted, and I have a grid of size 5 cross 5. So this is L equal to 5 here. And now the qubits are sitting on the edge. So each of these circle is a qubit, and I have two different kind of important figure or structure, which is called placket. That is the face. This is also called face. And I have the vertex. And the vertex is this thing here. Now the idea is if you have a L cross L toric code, there will be two L square edges. This is easy to see. So this means there are two L square physical qubits, or these are the data qubits. And now there is also periodic boundary condition, and now we come to the idea of what are the stabilizers here. Because we have seen that defining the stabilizers basically define a code space, so we will discuss the code space by discussing the stabilizers. So as you can see in the figure, the plackets and the vertices are basically the stabilizers. So here I have a stabilizer that is of Z form. So all the plackets are the Z stabilizers, or these are also called faces. And there is L square face for a L by L grid. And all the vertices are also stabilizers, and these are also L square. And now the idea is to corresponding to every face you will have 4 qubits, and these 4 you can just assign them as data qubits D1, D2, D3, D4, and this is my stabilizer here, or this is my vertex stabilizer here. And like this you can have a lot of different stabilizers. You can take 2 stabilizers and multiply them. We will see some of that later, but the main idea is these are the generators that I am talking about. And how you can see that they commute, that commutation I am showing here. So they commute. So because stabilizers, they are an abelian subgroup, they should commute. And you can see that if I have a vertex and a Z or a placket stabilizer together sharing a particular vertex, then they differ on exactly 2 qubits where they differ by x and z. This means that they commute. By one of the videos we saw what is the basic criteria for Pauli matrices to commute or anti-commute, and using that they commute. Now let's come to the idea of multiplying the stabilizers. So in this case, boundary plays a crucial role. So what happens is, if you multiply two stabilizers, suppose this is stabilizer S1 and this is S2. So let me use a different color. So suppose I have S1 and I have S2. Then when I multiply S1, S2, I get a stabilizer that is defined by the boundary of S1, S2 jointly. You see, the center, the qubit at the center becomes identity because Z square is identity. And I get a stabilizer composed of qubits in the boundary. So this happens in general. Multiplying two or more plackets give the resulting operator on the boundary. So here I am multiplying this stabilizer S1, S2, S3, S4, and I can see that there is a boundary that goes kind of around the torus because of the periodic boundary condition. Now let's understand why there are L square minus 1. So there are 2 times L square minus 1 independent stabilizer generators. So why this is so is easy to see again, because product of all the L square plackets. So here suppose S1, so let me change the color. Suppose I have S1, S2 up till the entire thing SL square. Product of all these L square plackets give me the identity operator, and this means that it is not independent. The set is not independent, but I need an independent generating set. And this simply means that there is L square minus 1 generators. So the idea is I will not multiply one of the plackets. And this gives me L square minus 1 generators, and with a prefactor of 2 because I have the vertices and plackets and they both are kind of on an equal footing. And to understand why they are on an equal footing, it is easy to see the dual lattice picture. So the dual lattice picture for a toric code is a very helpful way to understand the loops and the product of X stabilizer basically. So here in the dual lattice, what happens is the lattice gets shifted by half a cell down and to the right. So this means now where I have vertices here, so these points will be occupied by a qubit. So you can see that there is a dotted lattice made in the figure, and the edges of this dotted lattice will take the qubits now once I go to the dual lattice space. So you can see that now what I will have is the vertex X operator will now become a placket operator. So this means in the dual lattice, what happens is that in the dual lattice, the Z stabilizers become vertices. So Z stabilizers becomes vertices and X stabilizers becomes plackets. So this is the main idea. And now, so there are 2L square physical qubits. There are 2L square physical qubits and this many generators. So if you subtract them, you get the number of logical qubits or the encoded qubits. So basically it is 2 for a general toric code. So if it is 2, it means that I have a 2 logical X operator and Z operator. So basically I will have a Z operator that acts as phase flip on the logical qubit, and I will have X operator that acts as bit flip on the logical qubit. And these operators should be undetectable because they change the span of the code, like they don't change the span of the code space. So they should better be belonging to this set, which is the set of undetectable error. So undetectable errors. So now this I have shown on the left hand side in the figure. So in the figure I have Z1, X1, Z2 and X2. As you can see that the Z operators, they kind of forms a loop. So this forms a loop around the torus, and X operator similarly forms a loop around the torus, but it is shifted by a half of cell length. And it is easy to see that these operators satisfy the anti-commutation property because they exactly will overlap at one place where they will be different, and this means they will anti-commute with each other. This is what we need, that the Pauli operators anti-commute with each other. So with this we have come to the idea of what is the code distance. So the code distance is this many physical qubits encoded into 2 logical qubits, and it corrects error of length L. So in this length L error, so that's not right. So the idea is this is the minimum undetected error. So this is easy to see again, because look at the Z1 error. The Z1 error is such that the Z1 error is such that it is of minimum length L, and it encircles the torus vertically or horizontally. So and this error is undetectable because it belongs to the normalizer minus the group. So here I am showing that this is the Z1 error. So this is Z1, and this is, I am showing how you can multiply a stabilizer placket to the Z1 operator. So you can have S1 times Z1, and by this you can just shift the loop. You can just deform the loop, but it will still loop around. So that's the main idea. And now let's go to the error correction criteria and syndrome extraction. So the idea is that how we can detect the errors using the stabilizer. So this is also interesting. The idea is first to consider a Z error. So suppose here I have a Z error. Then you can see that these vertices which are in blue, they will register a anti-commutation relation. So they will register a -1, and this vertex is some X vertex, and this is also an X vertex. Now if I have a X error, then these plackets will register a -1, and this is some Z placket, and this is also some Z placket. Now what happens if I have two Z errors? So I have one Z error here and another Z error here. Then you can see that the boundary of the error will actually register a -1. So this X placket and this X placket, which is drawn in blue, they will actually register -1. Similarly, if I have two X errors, then this Z placket and this Z placket registers a -1. So this is true actually in general, where the boundary actually plays a very important role. So the boundary actually shows which plackets or which vertices will actually anti-commute. So a very interesting example is here. If you see this, here you can see that I start from this Z, and the error goes all the way up till here, and this is kind of a single loop if you see. So it is looping around the torus, and this is the boundary. The boundary is just 2 points, the starting point and the end point, and these two so there should be a circle here also, a qubit. So these 2 points will actually register a -1 and will anti-commute. So with this we come to some almost the end. The idea is now to understand how you correct the errors. So given the syndrome, you can perform the operation again. Like if you have a Z error or a X error, then you can write X square equal to identity. Or what you can do is you can correct equivalent errors by using the idea of the stabilizers. So suppose I have this error which starts here and loops here. So here there is a loop, this entire thing. Then this vertex and this vertex in blue, they will actually register a -1, and I can either apply this, or what I can do is I can complete this loop entirely. So what does that mean? That simply means is to complete the loop like this. So you can see that the loop that goes here, it completes back, and this entire thing is a stabilizer. So this entire thing is a stabilizer. This means something like that I have shown here. If you have a state and you have a error E1, if you can produce another error E2 such that the product lies in the stabilizer, this is correctable. So this is the idea of equivalent loops being able to be corrected by using errors. And I will end it with the idea that there are different classes of equivalent loops based on the topology of the torus, but we will not go into the detail. I will just highlight that this idea that this loop, this is not a loop, this is just a boundary, like this is just a line. So this line, then I have this line that encircles the torus. These belong to different equivalence classes. So you can encircle the torus in different way. So in the torus, you can either encircle it horizontally or vertically, or you can encircle both horizontal and vertically, or you cannot encircle. So these are like various groups: 0, 1, 2 and 3. So with this I end my video. So this was a brief overview of the Toric code and what are the stabilizers and things like that. So let's go to the next video.